Quantum mechanics, just when you thought it was safe to enter the universe. Physics 133, 152 edition. These are some alternate titles. You might want to just pause it right here and just take a look at them, but I'm just going to move on. I do want to point out that light and electromagnetic radiation are pretty much mean the same thing. They do mean the same thing. But light generally in everyday vernacular means visible light, but we are talking about a much broader definition of light. I think this quotation speaks for itself. You might want to pause it and read it. All right, so there's something known as the Copenhagen Interpretation, and there are some basic principles here that are used throughout. Copenhagen Interpretation is not necessarily in favor with everybody. This is basically what I was taught, although there are some people who disagree with it. The hidden parameters or hidden variables is something that there have been various physicists who have sort of gone against the idea that they do not exist. And that's, to me, that was the main exposure of where there's disagreement. A guy named David Bohm was big into the hidden variables, and so he was basically not considered in the mainstream for his belief on that. Just as a side note, one of the professors at University of South Carolina when I was there was Yakira Haronoff, whose dissertation, so his doctoral dissertation, was potentially worthy of Nobel Prize. It's been mentioned several times. He was one of David Bohm's students. David Bohm was his dissertation advisor. And so it was thought that one of the reasons why Yakira Haronoff had not won the Nobel Prize yet was because of his association with David Bohm. True or not, I don't know. Classical physics is what you have been studying for 2 semesters now, and so these are some of the things that have popped up. It was thought in the late 1800s that physics was almost done, that they had just to narrow down, take it out to the 6th decimal place, and to coin, I think it was Lord Kelvin. There was a famously and maybe apocryphally physics professor at Harvard who was encouraging his best physics students to go into engineering because physics was almost done. There wasn't much there. There's just, cleaning up this kind of stuff. And then 1905, special relativity comes out, and then within the next 10 years, quantum mechanics comes out, and physics changed dramatically at that point. Now, blackbody radiation. So you take an object, think about black absorbs radiation. That's why it's hot. And so one of the things is you take a black body and you hollow it out, and so with a small little hole, so it absorbs everything except for that which can escape. And so they looked at the radiation that was escaping based on the temperature and the frequency of what was coming out, and they came up with these graphs right here. You have classical theory or the Rayleigh-Jeans law. Those are the same thing. These are the spectrum that you saw, and it wasn't understood about why. And this was the sort of the birth of quantum physics when this gets resolved. I do want to point out that on the right-hand graph, you have that in the Planck's law, the 8 pi, that is a nu squared over c cubed. That nu represents frequency. I've talked about that in other videos and in class. That's just one of those things. It looks a lot like a V, but it is a nu. Nu. One of the uses, if you look back at this, you have the plots there on the left-hand graph where you have the different colors and the temperatures. That peak is what you are seeing, and that can basically tell you the temperature of something by looking at what the major frequency of light or wavelength of light that is coming off an object. And so this is how we know the temperature of the sun, as well as there are various pictures of people, sort of their heat prints. This is what allows us to know the temperature. Some vocabulary here, and I would not say that this is something that you have to memorize or anything like that, because as soon as I go to the next page, I'm going to forget what the vocabulary is. I have this in here mainly because when I look at the graphs, I've seen several variations of the graphs, and they all seem a little bit different using different vocabulary. And so I just wanted to get some documentation of the vocabulary there. So we have various models here, and that we're trying to explain it. Rayleigh-Jeans law is the one that produced the model that really did not work. That was the ultraviolet catastrophe. It was basically realized that, or in classical theory, every energy is possible, and so you end up with an infinity, to really put it very quickly. So Max Planck comes along, and first he does just a mathematical fit. He saw the curve, came up with an equation for it. I've done that before. Took it the next step. I did it with, I think it was a splash pool, of the depth of a splash pool versus the height. That was years ago. I just happened to be looking at this formula and noticed the curves were similar, so modeled it. But he just basically did the math fit without any explanation why. I mean, this is something similar to what Kepler did, although Kepler was dealing with far more abstruse information. And then he assumed not all energies are possible. Now, there is a derivation of this that I do not have in this presentation, so that will show up for another one. That's probably a 252 presentation there. But he comes up with this equation here, and then you have this thing called Planck's constant. And the units there are joule seconds, and I think this slide speaks for itself. So now we get into the other thing. So the first one, the idea that energy is quantized, becomes huge. And so now we're using that to relay into the photoelectric effect. Basically, you shine a light against a metal, and then electrons come off of it, and a current's produced. That's the essence of it. When you shine the light on it, that if you have a current going, if you increase the intensity of the light, you have a bigger current. However, if you don't have a current and you turn on the intensity of the light, you still don't have a current. The frequency of the light affected how fast the electrons ejected were, and it was almost instantaneous. There was no buildup of energy, as stated in number 3, and as implied earlier and stated in number 4, that there is a threshold frequency below which that the electrons will not be sent. If light is a wave, as it is in classical physics, there are certain properties, the interference, diffraction, refraction, and polarization. The links here are to classes that I've done for potentially another group or for this group, depending upon which class you are, where I go into detail about what these are. Interference basically is light interferes with itself, constructive and destructive interference. Diffraction is you have a small hole and light goes through it and basically waves out. You sort of picture if you had a water wave coming in and a wall with a small hole in it, that water would seep through the hole and the wave would continue out from that hole. There is refraction, which is light bending when it goes from one medium to another, and then polarization, where you can filter out light based upon the orientation of the electric field. These are all classic wave properties, and light has all of these. This is why light was thought to be a wave. However, if light is a wave, then we should just be able to have a greater amplitude of the wave to have more energy, and therefore that should be able to eject electrons. And there's the math behind it, where I derive for generic wave, total energy is related to the amplitude squared. And so just increasing the amplitude should be sufficient, and that doesn't happen. All right, so Einstein comes along, and he takes the idea, says, suppose the light is behaving like a particle, and that the energy is dependent upon the frequency, and everything falls into place. So you might want to pause it and read through this. And so now we have this idea that light has a wave property and it has a particle property, and which one it is depends upon which way you're looking at it. So oftentimes it looks like a wave and its wave properties, and sometimes, like the photoelectric effect, you have to look at it like a particle. And with properties of both, it opens up this whole idea of the wavicle. Issue number 3, Compton scattering. If light can behave like a particle, then can we treat it like a perfectly elastic collision? And so he goes through and figures out what is the momentum of light based upon the frequency, and then sort of extrapolates from there. And there is math involved in this. I set up the equation. We can derive that. The math is not particularly difficult. It's just not in this presentation yet, to be finished later. But it is just a little bit of algebra, a little bit of trig. Boom, you're there. I'm going to skip over this one and that one. They'll be dealt with later. The discrete spectra. I do have a video where give you an example of discrete spectra. It is based upon the way electrons are in an atom, and so that's why we then talk about the atoms here. And you can pause, just go through, nothing earth-shattering of what they believed about atoms here. The original model assumed that the positive fluid that was holding the electrons in was just more like a soup or pudding, and the electrons were like raisins inside it. And you can go through the math, and I think I actually do the math on this one. Yep, there's the math. Then I go through and derive what would happen. But if it's a soup and electrons are relatively light, if I shoot something heavy at it, what they called alpha particle at the time, but we now know is a helium nucleus, if you shoot an alpha particle at it, it should be so much more massive than an electron, which it is, and there's nothing to stop it. It shouldn't deflect very much. It should, if I shot it at another atom, it should just go straight through. And in fact, it doesn't always do that. And this brings in Rutherford. When Rutherford did this experiment, I say he did this experiment, he did think of it. I mean, that was his push behind it, but the people who actually conducted the experiment were his grad students, one of whom was Geiger. And so you can imagine sitting in a room looking for little bits of, trying to figure out some way of counting radiation coming by. Presumably it was an inspiration for Geiger to create his Geiger device. Now, one of the things about Rutherford, he never actually won a Nobel Prize in physics, which I think is a shame. He did get one in chemistry, but he also said at some point that all science is either physics or stamp collecting. He also said the fastest transformation he's ever seen was when he suddenly became a chemist. So he thought of himself as a physicist, but he didn't quite get the honors directly there. However, I think 9 of his grad students, over the course of his career, 9 of his grad students ended up getting Nobel Prizes. So he was definitely one of the movers and shakers and part of the powerhouse behind British physics at the time. So with this idea of a nucleus and the electron going around it, we can now start doing some analysis here. And the essence of the problem is that if an electron's moving around, it's accelerating, because it's not traveling in a straight line at a constant speed. It's accelerating, and therefore the electric field is changing, and matter of fact, it's oscillating. And if the electric field is oscillating, then that means a magnetic field is being created, and we should be getting radiation coming off of it. If radiation's coming off of it, it's losing energy, and if it's losing energy, the electron should crash into the nucleus. So Bohr comes along. He was one of Rutherford's proteges, and comes up with speculation. Now, I don't know, along with a number of other ones, I don't know where they started with this, because presumably he worked on it for years before he came up with these proposals. However, this is generally the text that I see when they talk about it. They give this proposal as if this was a starting point. And I suspect he came up with the answer and then came back with, hey, let's make these assumptions. You might want to pause, take a look. But the big thing is the quantized orbital angular momentum. Now, before we had quantized energy, now we have quantized angular momentum. And so here is the math behind it and developing his formula. That in there is the first quantum number. If you've had chemistry, they've talked about quantum numbers, that no 2 electrons can have the same quantum numbers, the same set of quantum numbers. There's 4 quantum numbers at this point, and he came up with the first one. The other 3 would require analysis of the hydrogen atom, and I may comment on this later, but that is, the scope of that is well beyond the course. More of the math, and basically this is the derivation of the energy, the negative 13.6 electron volts over n squared, and that matches observation. And so the discrete spectra that you see, if you watch that video, we could actually pinpoint exactly where that is based upon various combinations of n. So when n goes from 2 to 1 or 3 to 1 or so forth, it produces light of a certain caliber. And so here's one particular prediction. Now, one of the things is that the electrons are sitting down in the lowest energy level normally. You zap it with radiation, and the electron jumps to a higher level. And then when the electron, and notice this is different from what Compton was saying. When Compton's deal was is that the electron gets enough energy that it leaves the atom completely. Now we are talking about the electron gets enough energy to stay within the atom, but it's just a different orbital. So it goes to a higher orbital at a higher energy. It's not stable there, so when the electron comes back down, it's going to emit radiation of a particular type. In the example I give right here, it's going to produce this red light. And now, we started with a question. We started with this idea that light can behave like a particle. So can particles behave like waves? And so DeBroglie, in his doctoral dissertation, as one professor said, it was a tiny little thing. It was about 34 pages long, and he goes on this speculation, and he happened to be right. And so this is just an amazing bit of guesswork, but that pretty much sums up quantum physics. So here's the general, the one sentence version of his dissertation. It says that particles, based upon the momentum, you can figure out what the wavelength is. It's just that your momentum is so large compared to Planck's constant, as if you notice in the formula there, lambda is equal to h over p, that it's just way too small to detect. However, electrons are a different matter. Enter the Davisson Germer experiment, and similar to the diffraction patterns of light, where you send light towards a double slit, you get a diffraction pattern. If you watch one of those videos on diffraction, you'll have seen it. As well as if you hold your hand up to the light and you put your fingers together so that there's a small little crack between them for most people. I think it's most people. And you look at it, you can see these little black bands in the small gap between your fingers. That is known as single slit diffraction. It's the similar type thing, showing properties of waves. And here we can do it with electrons. And there is a video that I have, which actually there's a series of them that these people produced that I would highly recommend. Back to the Copenhagen interpretations there, that 3 and 7 are both sort of demonstrated here. Because when the electron gets sent, if you send it one at a time, basically you don't know which slit it goes through, and so the wave function must, as we'll talk about later, the wave function must include the fact that it goes through both slits simultaneously, or it goes through one or the other, or both. Similar to what we'll talk about later, Schrödinger's cat, it's alive and dead at the same time. So it goes through both slits and interferes with itself, but when it hits the screen, the wave function collapses. And again, some of this language we'll talk about later. The wave function collapses into a single point, but until you observe it, both situations must exist. And so this was also a big boost for the idea of the wave function and its interpreting later. Now we have the big year here, where we have 3 different sort of branches that they're mixed. They're just different ways of looking at the same thing. We will talk about not the matrix mechanics, but we will talk about Heisenberg's uncertainty principle, and then we'll talk about the wave mechanics and the wave function, which was a big Schrödinger thing. We will avoid quantum algebra. That is well beyond the scope of any physics class being taught at Forsyth Tech. I do want to point out just one little anecdote about Dirac. Supposedly he said so few words that his students came up with a new unit called the Dirac, which represented 1 word per year. The uncertainty principle. We have a wave here, and if that's a regular wave like that, then I should be able to pull out a ruler, tell you what the wavelength is. But if someone asks where's the wave, I couldn't pinpoint a spot. The wave exists everywhere. However, if the wave looked like that, I really couldn't tell a wavelength particularly well, but I could have a much better idea about what the particle is. And so we get this duality here of the more I know of one thing, the less I know of another. That is the essence of Heisenberg's uncertainty principle. So there are a couple of different relationships here. Action is a term that we never really have gotten into, but it is a physics term, thus the physics t-shirt that I saw once of physics, where the action is. It has a specialized meaning that's based upon energy for another time. Now we will derive the first one of those coming up, but it does talk about the more you know of momentum, the less you know of position, and vice versa. The more you know of energy, the less you know of time, and vice versa, and so forth. Now we're going to get into the derivation of the more you know of momentum, the less you know of position. And that's the first part of the joke. You might want to pause it, and then after you finish laughing, you move on. There is a far more complex derivation of this relationship here. This is just to give you a general idea, and there it is. This is the one that most beginning quantum textbooks will give you. It is what it is. But I'm going to go through it, just sort of get a basic gist of what's going on here. Now, as Robert March talked about, the absurd logic in coming up with this stuff, and so we have a little bit more of absurd logic. Now, part of these people have such a gut feeling. If you understand it well enough, you start developing gut feelings, and you might not know immediately why it's so, but you just believe it to be true, and then you just run with it. This is a big difference with math. Math, you have to show why it is there. Physics, you can always just take a wild guess and then hope experiment backs you up, and that's how we get a lot of this stuff. I do also want to point out the symbol for the wave function. I use a capital and lowercase psi, and it almost looks like I'm just randomly picking them. Technically, capital psi is the wave function for an entire system, whereas lowercase psi is for a particle, similar to big Q, little q for a collection of charges and a single charge. For the most part, later on, I just use a lowercase psi because I'm talking about a single particle, and that's why that's there. Lowercase k, the wave number, the fact that lambda equals 2 pi over k, that is related to some of the stuff that was done this semester when we dealt with deriving the speed of light. That is when I first introduced the wave number, and you might have seen it in class also. And ultimately we end up with the time-independent Schrödinger's equation down there at the bottom. Now this delta squared over delta x squared, if in the calculus version, those would be del's instead of deltas, and a del is just indicating a partial derivative. If you don't know what a partial derivative is, relax, but it's basically looking at the curvature of the wave function with respect to position in this particular case. The negative h bar squared over 2m del squared over del x squared, that is known as an operator that exists sort of and by itself, and you apply that operator to psi to produce something. But we end up with basically a second derivative must be related to the function itself more directly so that you can cancel it out. We dealt with this with harmonic motion. And so very similar type derivatives, and so that's why we're dealing with sines and cosines a lot. There are other functions that do that, but sine and cosine are this big one. One other idea behind it is part of the Copenhagen interpretation is that the wave function is indicating some sort of probability. And so when I basically do integrate psi star psi, and that's I know it's a calculus equation, but when you add up all of basically multiply the wave function by itself, you look at how it applies to infinitesimally small parts, and you do that over an infinite number of small parts, the essence of integration. What you end up with is that the total probability has to equal 1, which is 100%. And so this is employed later on in something known as normalization. That's the Copenhagen interpretation. We're dealing with item 5. Schrödinger's cat. You have a cat basically trapped in a well, and there's a little bit of a tiny bit of radioactive substance, so that there's a 50% chance that atoms will decay and 50% chance that it will not. So if it decays, then the cat's going to die. So the question is, after an hour, is it alive or dead? And the physics interpretation, the Copenhagen interpretation, is that it is alive and dead simultaneously, and it's not until you look that it becomes one or the other. So quantum physics says you must take into account the wave function must include everything until you know otherwise. And that's the second part of the joke, and then when you're finished laughing, move on. All right, so we're back to here. How do we actually work with it? And I'm going to take you through a couple scenarios here. I'm going to hand wave through some of the math here, especially since there's some calculus involved, but hopefully you catch the essence of it. So the free particle, we are just basically dealing with a particle that's, in terms of the universe, in the middle of nowhere. So there's nothing acting on it, it's just moving. And so we have a very boring situation here, but we do have a process here where we come up with an equation for the energy, which is based upon the wave number. Not a particularly exciting example. Now we deal with the infinite square well. So just imagine a really infinitely deep well, and there's a particle trapped in it. So now we actually have boundary conditions, because at x is equal to 0 and L, this particle cannot escape. And so we have to employ those boundary conditions right there. Work your way through the math. This is all doable for you. About in the middle where I talk about using other boundary conditions, I have KL is equal to n pi. N is an integer. I didn't state that explicitly, but n is some integer. It is not the same n that Bohr used, even though you do end up with an n squared. It's just coincidence. And this gets into the normalization. So as I mentioned, I do hand wave over the calculus here. If you have had calculus, you might want to go through as an exercise to try to figure it out. But this is how you actually come up with the wave function for this particle in an infinite square well. And the visual, that's my attempt at drawing various harmonics. But as the energy increases, you have more complex waves, as well as a higher energy, and that's why you generally draw it going up. Properly, if I had done this, that n is equal to 1, at n equals 2, that should be 4 times the energy of n equals 1. N equals 3 should be 9 times the energy of n equals 1. And 9/4 the energy of n is equal to 2. My drawing's a little bit off in that respect. Finite square well gets into the more interesting things here. We have this step function right here, and so to the left of x is equal to 0, when x is less than 0, we have the free particle, and to the right don't. And so mathematically, it doesn't stop. It can exist in the v equals v naught area, whether the energy is greater than it or not. Just that if the energy is below v sub 0, then as the wave function hits the barrier, the wave function still exists. It just starts to diminish and become smaller and smaller. But that has the implication of here, where we have a finite barrier where it is not 0 when it gets to the other side of the barrier. Matter of fact, the smaller L is, the more apt it is for this function to exist on the other side. You'll have a greater amplitude of the wave function, and therefore a greater probability that it will exist outside of it. So if you are, let's say, on one side of a hill and need to get to the other side, there is a non-zero probability that you will suddenly, what's called quantum tunneling, you will appear on the other side. And there is a video there that I recommend that you try. And so now if you think about the finite square wells, and think of an atom sort of the bottom of this well here, and you can have the atom appear. So the energy levels will be, for the low electrons, will be within the well, but at some point the energy will be off so that it might be outside of the well, and you suddenly end up with a sea of electrons, or the electron sea. And so this is why you have nice, easy conducting. And then the hydrogen atom, I at least introduce. From the hydrogen atom, you can derive all the quantum numbers, but beyond the scope. And I think that's it.